Hi, my name is Jim, and the topic of discussion today is frequency multipliers. What are they and why do we need them? Well, many times we need to have very stable frequency sources, say in radio and microwave equipment and so forth, and the way we would do that would be with a crystal oscillator. Now the problem is that as the frequency increases, the physical size of the crystal gets very, very small. It's hard to maintain accuracy, it's very delicate, and also very expensive. So we can obtain that accuracy if we use a lower frequency crystal and figure out how to multiply that up to the desired frequency of interest. So to explain that concept, we're going to start out here with basically a tuned circuit. I've used a bipolar transistor, and I'm working with a tuned circuit here with 100 kilohertz. Coupling capacitor input, so the DC from whatever is feeding this does not upset the bias on the transistor. I call this V in and V out. And let's just take a look at several scenarios with regard to the input signal. First, if we have a sine wave input, looking at this in the frequency domain, we see a single spectral spike. Now in the frequency domain, any spectral spike is a sine wave. There's no such thing as a triangle wave or whatever in the frequency domain, because this is displaying the signs that make up more complicated waveforms. And here we would have the sine wave down here represented by that 100 kilohertz. What we see in the output, not surprisingly, is an output of 100 kilohertz, and the gain of the transistor is probable that the amplitude would be higher. So that's kind of a straightforward case. Now let's take a look at feeding in a sine wave at 33.3 kilohertz. Well, what's going in is a single spectral spike, and we don't have any input components sitting up here at 100 kilohertz, which is what our tuned circuit is set for. So we wouldn't have any output except for maybe some little residue coming off the tail of the tuned circuit. So a sine wave going into this circuit at 33.3 repeat kilohertz would not produce any appreciable output. Now here we're also assuming here that we have a reasonable Q, its quality factor, which is defined by the reactance over, in this case, the winding resistance. And the reactance at a Q greater than 10 of an inductor and a capacitor has the same magnitude. So we're not dealing with a peak circuit, it's actually a tuned circuit. So not too much thrilling there with a sine wave, but let's move on a little bit. Here's our frequency multiplier from the previous page, and now we're going to input a square wave. So suppose that our square wave is input at 100 kilohertz. Now what we know about a square wave, meaning it has a 50% duty cycle, is that there are no even order harmonics in the square wave. So the second is going to be 0, we have a third, fourth is 0, we have a fifth, sixth is 0, and so forth. So if we feed this into our frequency multiplier per se, what we're going to get is a single output spike at 100 kilohertz, and this will be a sine wave. Because all of this stuff makes the square wave from a fundamental sine wave at 100 kilohertz. All the harmonics are filtered out. What's left? The fundamental sine wave at 100 kilohertz. So that's an interesting thought. So let's feed in a square wave now at 50 kilohertz. See what happens there. And our second harmonic is going to be 100 kilohertz, third is 150, and so forth. And since we don't have any even order harmonics in a square wave, 50% duty cycle, we see that there's no energy here at 100 kilohertz. What's the output going to be? Basically 0. So no energy at the resonant frequency. The filter will basically not pass anything. And then finally, if I can get this page opened up. There we go. Almost. Take a look at a square wave at 33.3 repeat kilohertz. Well, there's our fundamental. Second harmonic is nothing there. Third harmonic is 100K, and we do have something there. Fourth harmonic, fifth harmonic, and so forth, and we're feeding this into the frequency multiplier, and this little guy right here is going to be able to be filtered by the tuned circuit, and what we'll see coming out of that is going to be a 100 kilohertz sine wave. So it's taking the third harmonic of 33.3 kilohertz and selecting that to be the output frequency. So effectively what we've done here is we've multiplied the input frequency by a factor of 3. Likewise, we could have the output tuned to the fifth, 166.6 repeat, use the fifth harmonic if we wanted to do that. So, and again, the output is going to be a sine wave, single spectral spike. So let's look at something a little bit different other than square waves, and we'll start out with a rectified sine wave. Kind of looks like this, and we'll let this frequency be 50 kilohertz for the heck of it. And with this particular signal, there aren't even order harmonics. So we get a fundamental component here at 50K, we have a harmonic here at 100K, another harmonic at 150K, and we feed this into our frequency multiplier. It's going to take the 100K input component, select it and amplify it by its tuned circuit, and then the output of this would be a sine wave at 100 kilohertz. So, and this also has a DC component too, but we don't care about that because we're blocking DC right on the input stage anyway. So in conclusion, make a frequency multiplier very easily. It's just tuning the circuit to the frequency you want and then feeding into it something that's a sub-frequency of it that's distorted. It has a harmonic component at the frequency of interest. And then that tuned circuit simply eliminates every other thing, and we get out what we want to get out, which in the case of this example would be 100 kilohertz. So that'll conclude, and thank you for watching.